Okay, so last time we were left with the wave equations. So I guess I maybe just went too hurry last time. I didn't get into some details. I'm not going to like show you any, arithmetic process, but intuitively, I said this equation is derived, right? This is the acceleration and this is the force. So we use the Newton's second law is F equals ma, right? F equals ma. And just intuitively thinking this is a, right? This is acceleration, and m is some constant, and f is somehow equivalent or proportional to this term. Okay, so this term is the concavity of the stream, because we know when we create a wave on the string, right? This is a waving string. The more deformation happens is here, right? The more force it suffers. So here there is no deformation. It stays at its equilibrium, so there's no force. And so here is a little bit deformation, is a little bit force. So the force is somehow proportional to this concavity. So this is just some intuitive explanation, which means the wave equation is derived from the transmission material with elasticity and inertia. For more detailed or more precise model, I think you can refer to the stream model here. Right, so this is derivation using the stream model. So there, I will go through this process maybe a little bit later on when we talk about some other slides. But here, if you can read mathematical annotations and differential equations, I think this is a good process for you to go through. So I'll get in a little bit into the process later on. And for the spring model, because we know the spring is also some material with elasticity, right? Follow the theory of elasticity. So we can derive the Hooke's law is F equals kx. Okay, and you use the formula F equals kx. You can derive this formula, and you do some equation manipulation, and then yeah, you can get the expression of the derivative. Because I don't know if you really have the background of derivative calculus and difference equations, so I'm not sure how far we should get into this topic. But to get a good intuition, right? So we are talking about intuition in this lecture, but we want our intuition to be correct. We don't want to be something just ad hoc, or I just tell you some theory and you just believe in it. So there is a precise mathematical model. You can describe the process. And today I will also introduce you to some numerical simulations and showing that using this kind of physical model, we can really reproduce the sound. Okay, so it somehow demonstrates this theory is true. So we have this theory, and if we follow this theory, we do the same process and we can produce sound. Okay, so this will be the last part of this lecture. So now I want to pick up maybe a little bit. So last time we talked about this is the general solution of the wave equation, right? We didn't get into the derivation. So here is a very brief derivation. So it basically uses the separation of variables. So you rewrite the variable of Kc and neta using x and t, right? You see, you write x minus ct equals to this variable, and x plus ct is equals to this variable. So there is a change of variables. So your variables are changed from. So at first your variables are x and t, right? The position and time, and then using this formula, you are changing your set of variables to Kc and neta. Okay, so after changing this variable, you can rewrite the equation as this. So this is a much simpler equation, and you can see this is equal to 0, and then you can separate Kc and neta. So Kc and neta are independent. Okay. So from this equation you can derive that. Sorry, it's difficult to write like this. So Kc and neta are independent. Okay. From this, you can derive this relationship, and then you can separate Kc and neta here, right? You can write U as some function of Kc and some function of neta, and there is no interfering term or interleaving term of Kc neta. Okay, if they are not independent, there will be some other function, let's say K, maybe of Kc neta. Okay, that means there is some correlation between Kc and neta, but because they are independent. From this expression, we can write them separately. Okay, so there's no correlation, no relationship, between Kc and neta. Therefore, we can derive this. Okay, so Kc equals to x minus ct, and neta equals to x plus ct, and then we get this expression. And this is a general solution for the wave equation. Okay, so I think this should give you some more clearer explanation of the of why this is the general solution of the wave equation. And last time we also said we can check this, right? We can just compute the second derivative of this expression, and we can see it fits this the wave equation. So intuitively, this expression means there are two traveling waves, right? There are two traveling waves. So this means this wave is going to the right. This means this wave going to the left. And this is the initial value problem. What is initial value? So here the initial value gives you the when t equals 0, right? Initial value means when t equals 0 at the first initial state. This is a position, and this is the velocity. Okay, this ut means the first derivative with respect to t. So this means, for example, we have a string here, right? So the string now it's just in its original state. There's no movement, no vibration, and now we want to plug the string, right? So this string is plugged. So we are giving a force here, and this is our hand. Let's see, this is our hand, and we are plugging this string, and we are placing this string at this position. Okay, and now we will release the string from here. So we're going to plug, right? Plug the string. So we pull the string here, and we will release. And we will ask what's the movement or what's the vibration of the string after we release it at this position. So this solution gives us, right, the movement or the vibration of the string after its initial state. And if we insert this initial value, initial condition into this general solution, we can derive the D'Alembert formula here. Okay, so this is very easy. Okay. So here is the details, right? So you have the wave equation. You just substitute this initial value into the general solution, and you can get the D'Alembert formula. So this is the initial condition. Okay, and we will review this part of this video and give you a more intuitive feeling of what that means. Okay, so here you can see is the wave equation, and this is D'Alembert formula. And here the author actually gives you the box, some initial condition, and do a simulation here showing you what the wave will move after the initial okay. the initial condition. Let me see.
Time t equals 0, which is the same as the picture that I drew down here.
Okay, so this box is the initial condition. So let's say the string is placed like this. Okay, so there's some potential here, some energy here, and then if you release the string from this initial position, what will happen? Okay, what's the movement of the wave?
And as I play the animation, you'll see the two half-height boxes move away from each other at the speed c equals 1. So at the initial time, you see that the two half-heights add together to...
Okay, so you can see as the formula describes, there are two traveling waves, right? To the right, to the left, and to the right, from the initial position.
Be a total height of 1, but then they start moving apart. Now, if you think about it for a minute, you realize that the fact that I used a box function here is really just irrelevant. If g is 0, then the D'Alembert solution will just be this 1/2 times the combination, the sum of the two f's, one moving to the left and one moving to the right. So really, whatever initial profile I start out with, when I let the wave equation do its work, I'll just see two half-height f's moving apart in different directions. All right, let's do another example. Just in case you think now that taking g to be 0 is...
Okay. So the D'Alembert formula, which means actually your f and g can be any function. Okay. Maybe there are some constraints for the functions, but basically any shape of the function will serve the purpose. So it will work with any initial condition, and you can know how the string will move after this initial condition using this formula. Okay. So the first example, the user uses a box, right? A box initial condition, and here the author changed the initial condition to something else.
Let's take f to be cosine x, and you'll see that actually something kind of interesting happens. So our initial shape is just cosine x, and then the D'Alembert formula will say that u must be 1/2. Let's take c equals 1 again. Cosine x plus t plus 1/2 cosine x minus t. All right, so just two cosine waves moving to the left and the right. Let's see what that looks like. So here's the animation. We see the initial profile of just cosine x, and let's see what happens when we let the wave equation do its thing. So it's a standing wave. Maybe you expected that, maybe you didn't. It certainly doesn't look offhand like a sum of a wave traveling to the left and a wave traveling to the right, but that is what it is. In fact, if you remember your trig identities and you look up the sum identity for cosine, you'll see that this in fact is equal to the cosine of t times the cosine of x. And that looks a little bit more like the graph that we were looking at. It's the cosine x multiplied by this cosine t, which is making it oscillate back and forth. Since this is kind of an interesting example, I made another animation where we see in solid black the original function u, and in blue we'll see the left moving wave, and in red we'll see the right moving wave. Now the black line is the sum of the two, so it's the combination of the heights. So you see how this one standing wave can be a sum of two traveling waves moving in opposite directions. Okay, we've looked.
So this is the standing wave, and this will be the main topic of we are going to talk about musical instruments, simulation, and everything, one-dimensional waveform. So the standing wave will be a main topic of our first part of lecture. Okay. So before seeing that, so we know from the D'Alembert D'Alembert's formula, this is the initial condition. But what about the boundary condition? So here, if you have a string that is with fixed end, okay, so the left and the right, so these are the two fixed ends, which means they won't move. So this actually provides a boundary condition for the string movement. So think about if we don't have this fixed length, and then the wave will move, all the way to the left, right? It won't reflect back. But because we have this fixed point, therefore, when the wave moves here, it can no longer move to the left anymore, which means it has to move back, okay? It has to change its direction and move back. So if we don't have this point, the wave will continue to go this direction. But because we have this fixed point, the wave, you can see here, it reflects back. But why when it reflects back, it will change this direction, right? So now it's here, but now it's reflected back. No, from down to up, and here from up to down. So it changes its direction when it reflects, when it fixes this a fixed node or a fixed wall. So there are some physical tools to describe this. We'll get to this later on. But for now, I just want you to have this basic, image that when there are two fixed ends, the string, the movement will be like this. So this will the wave will be reflected at the fixed end. Here is the physical model of the string, okay, the movement of the string. So as before, so this is a string, and we at the initial condition is that we plug it, or we just pull the string here. So this is the initial position. So we pull the string here, and then we will release. And when we release, we don't give it any extra force, and it will move, in its own trend. So when we release the string, how the movement will look like is actually, we already know from the D'Alembert formula, there will be two traveling waves, right? There will be one wave moving to the left, one wave moving to the right. And then when we release the string here, it will deform like this. And then gradually this will be, so this is the left traveling wave, this is the right traveling wave, okay? So the wave will go this to the directions. But here, because we have this fixed end, x equals to 0 and x equals to L, then from this image, when the left traveling wave, when it hits this fixed node, it will be reflected. Okay, this will be reflected like this. This will be reflected back, and it's the same for the right traveling wave. When it goes in this direction, and when it hits this node, it will be reflected back. Right, and then this wave, once it's reflected, it will move to the left. This wave will move to the right, and the two waves will meet somewhere. Right, so the two waves will meet somewhere, and they will be added together. So it's a simple addition because we already talked about it's linear acoustic, right? They will be superposed upon each other linearly. There won't be any other nonlinear interference. So this is the movement of the wave, and this process will continue, right? Will continue means let's say there is no damping or no other friction. When this wave, right, once it's reflected, it will move to the left, and it will move until here. When it hits this node, it will be reflected again and move this, right? And then this is a periodic process, right? It will move to left, right, left, right, left, right. And like this image, it will be reflected all the time until, okay, so in the natural system, there will be natural damping. So the movement will stop at some point. But in this ideal condition, right, the string will move like this forever long. Yeah. Any question? Okay, so I hope this somehow makes sense. If it's not, we still have many other explanations. Okay, yes, I will reiterate it again and again and again, so that you finally know what that means. Okay, yes, difficult to understand at first, probably if it's your first time listening to this, but after 10 times, I would say, yeah, it will finally make some sense in your head. And here. It is the same, okay? So if, let's say you plug the string or you pull the string at the middle, okay? So this position is x equal to L/2, okay? If this is the middle point, you pull the string here and you release the string, and the string will right? Exactly like this. The string will move up and down, somehow like that. But actually, there are two waveforms, so there will be two traveling waves reflected back and forth, back and forth, back and forth. So, when t equals period over 8, it will be here. When it's 4, 1/4 of the period, it will be at the equilibrium, and when t equals half the period, it will be totally reflected. So yeah, I didn't find any animation about this. So here so here it's not an animation, but it's somehow a step-by-step illustration of what the wave looks like. Okay, so this condition is exactly the same as this one. And this is the time equal to 0. And after some time, the wave will be deformed like this and like this. And then at some point, it will be flattened. And then the two waves will be reflected. And so the position will be lower than the equilibrium. And then the two waves will move towards each other, and they will meet at each other, and this position is exactly the the opposite or the reflection of the initial position. So this is what will happen when you plug the string at the middle. Okay, so this is x equal to 0. This is x equal to L, and this position is the middle position, x equal to L/2. Okay, but what if you plug the string somewhere else? Okay, so let's say we don't choose the middle point, we just choose some other point here. Let's say we pull the string here like this. Then what's the movement, right? Because the left traveling wave and right traveling wave won't be symmetric anymore. Then what will happen to the string? What's the movement? What will the movement look like? So this is the one of the illustration here. So when the string is plugged as the 1/7 of its length, okay, so it's like this. It's in this position. After that, it's the same, right? We still have left traveling wave and right traveling wave. It's only in that the left traveling wave will hit the node much earlier than the right traveling wave. So when the right traveling wave is still here, still moving like this, the left traveling wave already hits the boundary. So it hits the boundary and it will be reflected. So the left traveling wave will be reflected first, and this will be reflected here and here and here, right? Until the right boundary is hit. So until the right boundary is hit and the wave is finally reflected here. Okay. So and they will be reflected and like this, and then the wave, so there's left traveling reflected, this is reflected, and then they will meet each other and they will continue to travel. Okay, So they will continue to travel here, and this will be reflected up again, reflected up, and here, and then it will somehow, after you can see one period or one cycle, it goes back to its initial condition. So after this process, so this is an illustration of two unsymmetric traveling waves, left to the right, left and right. Okay, so one wave will be reflected first, and the other will be reflected later on, but the movement is the same. Okay, the physical rule or the physical laws are the same. It's just they won't change the direction simultaneously. So here, when they hit this equilibrium, they are reflected at the same time. Therefore, they are, they change the direction simultaneously. Here, one wave changes direction first, and then the other follows. Okay, but the physical law is the same. It's just the reflection. Okay, the reflection of the boundary. Okay. So finally, we're going to talk about something about the standing wave. Standing wave is very important. So as you already saw in the animation before, so there are two like sinusoidal traveling waves left and right, and when they sum up together, this will be the standing wave. Okay, so I will use this link to talk about this. But why is standing wave? You can see the nodes, right? The right node here, they never move. They are zero forever. So these are the fixed point, and only other waves are moving. So you have a feeling that they are not traveling, right? They are standing there. They are staying there. So this is called standing wave, and this is the mathematical the description of the standing wave. So we'll get more into this now. So, okay. So there are two waves, right? At least we know there are two traveling waves left to the right. They are sinusoidal. Therefore, we are writing out the right traveling wave like this. Notation. So this is the right traveling wave, YR, and this is left traveling wave, YL. Okay, and they are of the form of sinusoidal. So we use sine. We can also use cosine, but they're they are basically the same. The only the difference is only for pi over 4 phase. So the only a phase term. So we choose to use sine here, and then for the traveling wave, we are going to add them together. Okay. So the right traveling wave and left traveling wave are adding together. And if you know the trigonometrical identity rules, when you add two sine together, okay, you can decompose them, right? You can decompose them. And this is what you will get. So adding the right traveling wave and left traveling wave together, this is the expression you will get. And this is the formula for the standing wave. This is called standing wave because we already saw in the previous, in this graph, you can see there are the fixed nodes, right? So where are the fixed nodes? Okay, let me see. So here, to compute the fixed nodes, we should look at this this formula. Okay. So this cosine omega, this is a function of t, function of time, and this is a function of x over the position. And we know for a standing wave like this, the nodes are here, right, at this position. So no matter how the time changes, this position will be fixed forever. This position will be zero forever, which means for these positions, actually the sine term, right? The sine term equals to 0. But when the sine will equal to 0, we know that sine is a periodic function, and when we want this to be 0, this should be lambda or 2 pi x over lambda, right? So this is this term equals pi n, right? Because for a sine wave, if you remember, this is 0, this is pi, this is 2 pi, right? So this is sine x. So for all the multiples of pi, 2 pi, 3 pi, 4 pi, okay? For all the, so n is any number, any integer. N is any integer. For any integer, any multiples of pi, the sign of this term will be 0. Okay, so if you want this term sine of 2 pi x over lambda equals 0, you want this to stand. And to compute this, let's say we want to compute x, and then it's equals and pi, so x equals to 2 over lambda n, right? And n is any integer, therefore this x can be 1/2 of the lambda. The lambda is the wavelength. 1/2 of lambda, or lambda when n equals to 2, when equals 3 is 1.5 of lambda, 2 lambda, etc. So this corresponds to the formula here. Okay. So this is when we take this term to be pi n, and then we can compute that x. When x take these numbers, they are the nodes. Okay, they are the nodes. The nodes means the right nodes in a standing wave. So these are the numbers we compute. So standing wave actually impose some boundary conditions, right? So the boundary conditions like this, which means as a boundary, when x equals to 0, and let's say this is x equal to L. Let's say the length of the string is L. Okay. The length of the string is L. And the boundary condition is that when x equal to 0, this is 0. When x equal to L, the position is L. So these are two nodes. These are two nodes of the waves, of the standing wave. Okay. And the condition is that this term equal to 0 forever, and then we have this equal to 0. And then we have this, right? I just did the derivation. Lambda equals 2 over 2L over n, and n can be any integer. Therefore, we compute the frequency or the wavelength. So you can see these are the waveforms that can be formulated on a string. Okay. So they are of different harmonics, but they have this integer relationship, right, among them, because this is the relationship of the nodes. So it's called harmonics because they are of the multiple relationships. Okay. So let's skip those things. Any questions so far? Okay. So let's see. This is the string, right? This is fixed length string. The string of length L. This is 0, this is L. And these two nodes are the fixed points, which means they are the nodes. Therefore, the only waves this can form are like this, right? Or this. Or this, okay? This is like what this looks like. So these are, because they are restricted by the boundary conditions, these are the only waveforms that can be formulated over the string. And this is where the harmonics come from. So when you listen to the musical instruments, right? You know there is a fundamental frequency and there are harmonics. So this is why the harmonics are formed. And sometimes you may wonder like why when you play a pitch, right? There is only the harmonics. There's no other frequencies. Let's see, this is the frequencies, and this is your fundamental frequency. Maybe let's say your note is C4, right? And you know, there are some harmonics of integer multiples of C4 that forms the color or timbre of the tune. But why there's no other, like, there are basically no other frequencies, right? Where are those frequencies? Why these frequencies are filtered or left out, and why they are not presented? So this gives you this explanation, right? When you have a fixed string, because many musical instruments are string instruments, okay? Even if it is pipe, it's the same principle, okay? For the pipe or bore or the string instruments. So for any instruments of this one-dimensional, okay, following this one-dimensional waveform, it is like this, okay? It has some boundary conditions, and then only fixed modes or fixed patterns can be generated. Let's say we have another wave of a different, okay, let's say this wave. Okay. So let's see this wave, right? This wave, it is not an integer multiple of the fundamental frequency, but it doesn't meet the boundary condition, right? So here it equals 0, but here it won't equal 0. Therefore, this wave will be naturally filtered out by this string because it doesn't meet the boundary condition. So this wave, this frequency will never cannot exist on this string model with two fixed ends. So now you may wonder, what if I don't have a fixed node, right? Sometimes we also have the open node. Actually, for open node, it still forms a standing wave. Okay, there are some. This will follow a different mode of moving, but it's still a standing wave. So here is the animation. So this node is fixed, but this end is free. Okay, so this is the free end. This is the open end. This is the closed end. So you can see when the node hits this fixed boundary, it reflects back, and this still forms this standing wave. So mathematically, how to describe this? Actually, the relationship is that at the free end, okay, at the free end, the derivative of y over x is 0. Okay. So therefore, we know the derivative of sine is cosine. Therefore, cosine is equal to 0. And we want this, if cosine is 0, then this term 2 pi L over lambda equals to 2 over pi. Not 2 over pi n, but 2 over pi 2n minus 1. Okay, why? Because cosine is of this form, right? It starts from here, it's like this, and here is pi over 2. Here is pi. Okay. And here's 2 pi. So for a cosine wave, if you want this to be 0, then it has to be pi over 2, 3 over okay, so it's always okay, 2, 3 pi over 2, or 5 pi over 2, okay, or 7 pi over 2. So therefore, so there will be 2, but this will be the odd number only, okay? Only the odd number, 1, 3, 5, 7. So this is 2n minus 1. So this is expression for cosine equals to 0, and if we no. Okay. Oh yeah. So we want to compute lambda. So lambda equals, so pi now here, right? Lambda will be right. If you just do some operation on this, this will be 4L over 2n minus 1 is the same like this, right? When n equals to 1, 3, 5 is the odd number. So this is the physical model for the standing wave with one fixed end. Okay. So talking about the pipe is the same. So because here it doesn't have more of this, let me go to here. Okay. So again, this is the string model. Guitar string, or the a string with 2 fixed ends. So it's mostly seen like almost all the string instruments. Okay, guitar. And what else? I don't remember the name of instruments, but yeah, just general string instruments with 2 fixed ends. Okay. So when we talk about the harmonics, what harmonics will exist on this model? Right. It will be half the lambda, 1.5 lambda. And sometimes this is open. Okay, let's see this one first. Closed open. So with one fixed end and the other end is open end. Okay. So actually the bore or the tube is the same physical model as the string. Okay. The harmonics, the number, the harmonics, the computation is exactly the same. The difference is that for string, the movement is given by the displacement of the string, but for this kind of tube or pipe bore instrument, the pressure is given by the compression of air. Okay, it's like the displacement of the air in the tube, but for string is the displacement of the string itself. So here you can see the only harmonics will exist is like this: 1/4 lambda, 3 over 4 lambda, 5 over 4 lambda. And there is also kind of a bore instruments with open ends, okay, with 2 open ends. So if it with 2 open ends, it will look like the cosine, right? And it will be 1 over 2 lambda, and 3 over 2 lambda with open end. So I don't know if it's clear enough, but I'll tell you a very easy way to derive those equations. Okay, so I personally feel this is a little bit, it's somehow complicated, this problem, but actually this is very easy. Here, let me tell you this trick. So thinking about this, you only draw a wave of a sine wave. Okay, so a sine wave is always of this form, right? And your wavelength is your period, basically, right? This is your wavelength, lambda. This is your wavelength. And then we know this is a node, right? For a fixed end, this is a node. And then the only harmonics will exist is here, right? You just cut it off on the node. Then it is half of lambda. This lambda, this is 1.5 lambda, 2 lambda, 2.5 lambda, 3 lambda, right? So this is yeah, when you compute the harmonics. So for a given sine wave, you only need to find the nodes, okay, where the sine always equals 0. So what about the closed and open, right? So you have one end is closed here, but the other end is open. Then you cut here, right? So this is 1/4 lambda, okay? 3/4 lambda, 5/4 lambda, which is right? It's given here, okay? So this is 1/4 lambda, 3/4 lambda, and 5/4, and it's 7/4, 9/4, 11/4. Okay. So for the open instrument, because you already know this left end is open, therefore you can also use a sine wave, right? Because for sine wave, when at this initial position, this will be 0. Therefore, you instead use a cosine wave. So you know a cosine wave is always of this form, right? And again, your wavelength is lambda is of this length. This is your wavelength. And now your another and it's also open, therefore just cut, right? This is 1/2 lambda, this is lambda, this is 3/2 lambda, 2 lambda, 5/2 lambda, etc. Yeah. So I think this is so there are many ways to derive those relationships, and they are actually indeed basically not that important, not that difficult, okay, relationship to think about. But the intuition is that it tells us if we have a tube like this, or if we have a string like this, let's see tube. Okay, we already saw too many strings. If we have a tube like this, we know it's restricted by these kind of relationships, which means only the frequencies, right? Only the frequency, because we know the L is fixed. Notation. We know that L is fixed. Yeah, this is a given instrument, and this you cannot change the length of the tube, and then you are computing the lambda, right? So lambda is equal to 2L here. Here the lambda equals to L. Here lambda equals to 2/3L. Okay. So only the waves can exist over this tube are only of the wavelength like this, or of the given frequencies. Okay. So you can see they are actually of integer relationship. They are the multiples of lambda. So this actually gives you why the instruments, right? Why the instruments have fundamental frequency and have upper harmonics, but they are of the given tune. So there is no like other frequencies interfering with the tube or with the pitch. Why every time you play the instrument, right, it will give you a steady pitch, like C4 or A3 or whatever, right? It gives you this pitch, this stable, steady pitch because of the structure of the instruments. Okay, the physical restriction of the instruments actually restricts the presence of the frequencies. So only in the so this is your fundamental frequency F0, and then you only have 2 F0, maybe 3 F0, right? 4 F0, etc. 5 F0. So they are the integer multiples of your fundamental frequency. So other frequencies here, so they will barely present. Okay. When you are playing some instrument, of this structure or of the string structure, whatever. So this gives you the pitch, and this is why the instruments can give you a pitch. Okay. So this is where probably, you know, where all the all the instruments and where all the music comes from. If we don't have musical instruments, we don't have music, right? I mean, pitch-based. If you play drums, like many African, you know, Afro-diasporic music, they are based on the rhythm. So they playing drums, playing the, you know, the claps, and these percussion instruments is a different story. But if you listen to the pitch based music, like the orchestration, like piano, you know, violin, flute, etc. So all the instruments are basically of those basic structures. Okay, either it's the string or the pipe, or it's, you know, a closed open, open, whatever. It always produces a standing wave, and the standing wave gives you a steady pitch because all the harmonics presented in this wave with given boundary conditions will be the, you know, the integer multiples of the fundamental frequency. So which gives you the pitch so that you can perceive this, you know, as musically, you know, musically interesting, and you can use those notes or pitches to compose. So okay, so I think this should give you a good enough introduction to the standing wave and how the musical instruments produce sound, and why you know, only the harmonics are presented. And when we later on, when we talk about the ratios and the consonance, dissonance, and the basic music theory, we will get back to this topic again. So music, right, is always, especially if it's pitch based, it's always about the harmonic, you know, the movement, like this, the harmonic relationships. So next, I want to talk about physical modeling. So in terms of this, right? So let's say now we already have the knowledge of how the music makes sound here, right? So because this course is about music technology, so traditionally before computer was invented, yeah, we have the physical instruments and we play the instruments and we make music, you know, physically. We use the real instruments. But now because nowadays more and more music is produced through the computer, and we also have the virtual instruments on computer, right? We have the virtual piano, virtual violin, and all kinds of sound. So one way of getting those sounds into computer is through recording, right? So you record this sound and you input this to computer and you replay the sound. But the problem is that if we know the principle, the working principle of instruments, is it possible that we produce sound using this kind of structure through the computer that can imitate or simulate the real musical sound, and we can use, you know, different parameters to manipulate the sound. So the idea is that we want to use the computer as an instrument, or we want to design an instrument using the computer, and we can play the computer. Therefore, we can. It's like we play a virtual instrument and we produce the sound. Okay, is that clear? Yeah. Yeah, I hope it's somehow clear. Because we talk about the physical modeling, it's like already over like maybe hundreds of years. But recently, because of the invention of digital computers, and we want to play sound through computer, and one way of doing this is that, you know, we use the physical modeling, something called physical modeling, and we imitate how the instruments make sound, make music, and we can simulate that using computer, and we can make instruments using computers. And when you play those tubes or when you play those parameters on the computer, you can generate the similar, like realistic sound, like it's generated by a piano, by a violin, or, you know, by any instruments. So this is what I want to talk about in this class. This material might be a little bit advanced, but I think the intuition is clear here, right? The intuition is that, right, you just want to use the computer to make some instrument and to make sound. So the method, simply speaking, is just generally use a traveling wave simulation. Okay, so we know the physical model of the wave of the sound wave is basically a traveling wave. Actually, two traveling waves, right? Right traveling wave and left traveling wave, and maybe they will be reflected and added together. So there are some manipulations, but the basic is traveling wave. So how to simulate a traveling wave using computer? It's actually carried out by something called delay-line. Okay, delay-line model. Delay-line actually simulates the propagation. Okay, what that means. Okay, let me find this annotation again. Okay, so we know if this is a sound source, and then this will emit sound, and the sound will propagate, right, through the transmission medium, this is the air, and the sound will propagate like this. But how to simulate the sound from here to here, right? We know the particle doesn't move, only the motion or the force will move. But let's say the transmission medium doesn't, display any kind of damping or reduce of energy. But this is not really true. But let's just assume, okay, in this ideal situation, let's see the sound here from here to here. It can be exactly right. It can be transmitted here, and it's exactly the same, because if there's no interference, when the sound propagates, the sound from here will propagate with no loss until this position. So these two will be the same, right? It just has some difference over time when it propagates. So this process of traveling or transmission or propagation is modeled by delay line. Okay, so delay line means it's delayed by m samples, which means there are some, let's sample this distance. So let's say this is m. Okay, so if let's say this is yn, then when it travels over m samples, this is y n minus m. Okay, so this is modeled by this thing called delay line. So here is a better illustration of the delay line. Right, when you input those things, yeah, it will get in like one over one, like it's the basic computer, like read and write, right? Using computer, the read and write. So this is the in is the read head. This is the out is the write. So read and write. So these are the pointers of the computer, and this is the how do you read in the delay line, how to write out the delay line. So this example, let's skip this. So here is the waves, right? So this is the stream model we just talked about. And we see in this real physical modeling, there will be two waves like this. And when it hits the boundary, right, it will be reflected. And when it hits again, it will again be reflected like this, etc., etc. But how to simulate this process using computer? Actually, we will use this thing called digital waveguide. Okay, so digital waveguide actually gives you two delay lines of the same length of the stream. So the two delay lines actually simulates the So this one simulates the left traveling wave. So this line is the right traveling wave. So they basically decompose the two traveling waves in the general solution of wave equation. And then when they travel separately and you simulate them separately, because they can be superposed, right? They can be added together. They are not interfering each other whatsoever. And then when you output it, you will add them together. Okay, you add the left wave and the right wave together, and this is your output. And at the boundary, because we know the boundary, this will the wave will be reflected, right? So here, oh sorry, so this should be the right traveling wave. Okay, this should be the left traveling wave. So here, when the right traveling wave hits this boundary, so it will be reflected back to the left traveling wave. And when the left traveling wave here hits the boundary, it will be reflected to the right traveling wave. Okay, and when it's reflected, it can be reflected, exactly without loss, or you can give it a filter. The filter actually means some damping or loss of energy, right? Because the wave, although it can propagate, but it won't propagate forever. So the transmission medium will take some energy out of the sound that will make the sound, become quieter, and finally the energy will just dissipate and the sound will disappear. So that will be simulated by some filtering, okay? By some filter or the damping coefficient, etc. So this is the basic model of the computer simulated, waveform or wave equation. Okay. I don't know if it's clear, but actually, if you just use this simple model, you can simulate a lot of musical instruments. Like actually, they simulated the 9,000-year-old Chinese flutes. Yeah, so this is use physical modeling. So you can use computer to reproduce these flutes. Okay, so this use the bidirectional delay line, and you can simulate clarinet reed, because we see that this model actually can simulate all kinds of one-dimensional waveform. Okay, not only the string, but also the pipe, the bore, the tube, and everything. All kinds of instruments can be simulated using this model. So they can simulate clarinet. They can also use the waveguide model to simulate, even syrinx, and you can also use this to simulate human voice. We call it voice synthesis. Okay, voice synthesis. So I'll show you later on of an interesting example of voice synthesis using the physical modeling that basically utilizes this kind of structure. Okay, the digital waveguide. And you can change in the parameters, etc., and the voice synthesis. Okay, so before I get into these the examples, so you don't need to do this by yourself, I guess, unless you are interested and you have the programming skill. If so, you can let me know, and I can give you some references or some materials. But yeah, I will show you in our second part of some examples of using the digital waveguide to simulate the sound of a human voice and the sound of the string and the piano. Okay, so before that, I think it might be helpful for me to go through something, we just talked about again, and maybe deepen your understanding of those topics. Okay, so this is motion for a wave. So you already saw this, and because I skipped this a lot, let me just give you some very brief illustration here. In case you're interested. So here actually you have the tension, right? This is a very small period or the, so this, let's see, this is your string, okay? And this part is taken from a very, very little piece, okay? A very little piece of the string, and you know, just use this microscope to see this. Okay, so this is a very small part of string. And then there are actually tension. The tension is at this end, so the string has two ends. And the tension here is like this, and the tension here is like this. And because this is a force, you can decompose this to, right, to x and y. Because the tension is like this, and you can, right? So this is ty, this is tx, and this is tx, this is ty. So in this model, because this theta 1 and theta 2, they are extremely small, because we are only taking a very small part here, right? Therefore, we can basically think theta 1 and theta 2 are pretty small, and they are subject to a lot of approximations. Therefore, we see this tx is t of sine x, sine theta 1 is approximately, oh no, cosine, because it's x, right? Tx is cosine, is basically equal to approximates t of cosine theta 2. This is for the, so we are seeing the force on this horizontal direction, so they offset each other. And for ty here, right? So ty is actually t of sine theta, and t of sine theta 2, t of sine theta 1 is the force of ty, of the vertical force. So the force is here, this force is here. So they give us the F. So Fn equals to t sine theta 2 minus t sine theta 1. Okay. And then we follow the Newton's law. So here actually they did another approximation, use sine, so which is sine and the tangent, you know, basically the same. So there's a lot of approximation to derive this formula. So so when you use the tangent to replace sine, and you get this kind of form, because tangent, right? Tangent is the first derivative of y over x. And then you use F equals ma. So this is a, this is acceleration. So m, the mass actually, okay, wait. So we are taking this small piece of string, and the mass here, so we have the unit. We see the unit is mu. So mu is the mass per unit length. And this string is of length d to x, okay? So not really d to x, but this length, but they just approximate because it's pretty small. And you just use d to x to approximate the length of this string. So m equals to mu of d to x here. Okay. So this is m, and when you take d to x, move it to the left, and you get this expression. And because delta m is the difference of the first derivative, and then this gives you the second derivative. Okay, you take the limit, it gives you second derivative of y over x, second derivative, and yeah, here is the acceleration. And this is a more like, you know, precise or a more standard way of derive the wave equation. So the result is the same, right? The result is the same as the wave equation. And we see there are traveling wave solutions left and right. So this expression is a little bit different, but it's actually the same. You just move c, right? Move c, just multiply c to the two expressions, and then you can get this is ct minus x. This is some paucity plus x, right? So it's yeah, it's the same as we just derived yeah, somewhere else. So this is the right traveling wave and left traveling waves. The traveling wave solution of the wave equation was first published by D'Alembert in 1747. So at that time, you know, it's only the physical modeling. But actually, this digital waveguide we are going to talk about. Okay. So the physical modeling digital waveguide here is actually developed by in Stanford's CCRMA, right? CCRMA. Yeah, it seemed like UCSD Computer Music. It's also a computer music kind of research center. So this kind of digital waveguide and physical modeling are largely developed, you know, in CCRMA in, I would say, around 1950. Okay. So it's actually not a quite old technique, but actually the waveform is quite old. Okay, it's like in the 18th century. So after 200 years, yeah, when the computer became like popular, people just use this model, use this physical solutions to, you know, to simulate the sound by computer. Notice the traveling wave solution of the 1D wave equation has replaced a function of two variables by two functions of the single variable in time units. Okay, so yeah, this is the change of variable. So sampling traveling wave, which only means, right, you make it the continuous wave become discrete. And this is the sampling. So this is not very important. Let's say the traveling waves. So damped traveling waves, right? So we see in the reality, in the real life situations, there is always damping. When something oscillates, it will finally, you know, the movement will finally terminate sometime, right? This is because either the air or the surface, it always have this friction. It will damp the movement, and the damping is actually simulated either by this coefficient or a filter. So because the different frequencies are actually damped at different rate, okay, therefore a unified coefficient doesn't really serve the purpose. That's why people use something called filter, digital filter, that can better simulate the different rate of damping at different frequencies. So this model is generally all the model we use, you know, to simulate instruments. It's a delay line model plus a filter. So delay line plus filter is the basic, you know, structure of doing this kind of simulation. Okay. Okay, let me see this reflection of spherical or plane waves. So there is something also called absorption, right? In air, there is always significant additional loss caused by air absorption. So which means when the sound travels in the air, it will absorb the energy, which is the same effect as damping. Okay. This called absorption loss. So yeah, what I really want to talk about is the reflection, because we saw the reflection, right, looks like this, but we didn't really explain why it is like this and why it changed the direction at the boundary, right? So here is some physical process or physical expression of why it happens. So consider the displacement of a string at the boundary x equals 0. So this is a fixed end, okay? So at the fixed end, the y always equal to 0. So the y is the left traveling wave equals to the left traveling wave, and x equals to 0. Therefore, these two waves, right wave and the left wave, they add up together, they should equal to 0 at this position. Therefore, the right wave is equals to the negative of left traveling wave. Okay. Then this is the reflection with a change of sign, right? This is a reflection of the change of sign, which means when the right traveling wave hits the boundary, it will be reflected, but at the same time, this will be the negative, right? Or the value will be the negative. And this is the why we are seeing this picture here. That's when this reflects, it will, right, change the direction, change the sign of the wave. Then what about the free end of the string? So why the free end is modeled by the cosine, and why at the free end the amplitude reaches the maximum, right? So actually, at x equals 0, if a string is free, there's no transverse force. So it means, let's say, we have a form like this, waveform like this, and this is the fixed end, and we know the other end is free end. Okay, so we previously we talked that when it is free end, it can only be like this, right? As the largest amplitude, it can only stop here. But the problem is, or the question is, why it cannot be anywhere like this, right? Why it cannot stay here? It has to be at the maximum amplitude. So the reason is that because if a string is free, there's no transverse force. Okay? No transverse force means actually the derivative here is flat. Okay, so the transverse force is flat. So at any other position, the tension will be like this, right? So there will be tension like, of this tangent. And then when you decompose this to the x-axis, there will be some transverse force. Only at this position, when the amplitude reaches the maximum, there will be no transverse force, okay, here. Therefore, at the free end, if we have the string of free end, right, so at the free end, this will always, for the standing wave, this will always be the maximum amplitude, okay. So yeah, this is exactly as shown in this animation, right? In this animation. So this wave comes in, and when it's reflected at the fixed end, yeah, so observed in this position. So this is actually at the largest amplitude. It's also at the largest amplitude at the free end. And mathematically speaking, we just said that the derivative should be 0, right? Derivative should be flat. Therefore, y over x should be, the derivative of y over x should be 0. And when we compute the derivative of right traveling wave and the left traveling wave, the derivative of x, yeah, so c is some constant, doesn't matter. And then we have this change of sign, right? Because there is a change of sign here. Therefore, this is minus, and okay, now this is correct, right? So the derivative is 0. Therefore, okay, this is 0. This c is constant, doesn't matter, and therefore y LT equals to y RT, right? Because this is the minus. Okay, this is why we derived this, and this is also the reason why when the wave comes to a free end, it will not change the direction. Okay, it will be reflected, but it won't change the direction. Which means that when the wave hits this is the free end, it will be reflected exactly the same way as it's propagated. Okay, it will be reflected like this. But if this end is a fixed end, if the wave comes in like this, it will be reflected like this. Okay, so this means at the free end, the reflection doesn't change the sign. Okay. Okay, so here the wave reflects back, propagates. Okay, so it doesn't change the sign. It's just I don't think yeah, maybe this is not a real good illustration of this process. But yeah, it just means the same way as the formula shows. So here we talked a little bit deeper on the reflection, the behavior of the string on fixed end, the free end, and then this is standing wave, right? Some animation of standing wave, right? Two traveling waves, when they add up together, it causes this standing wave, right? This is node, this is antinode. And this node antinode animation. Okay, so I think this is better one. Let's see, the wave hits the fixed end. Yeah, this is the movement, how the standing wave forms. Okay. What about the free end, free boundary? Okay. So here this free end. Oh no, sorry. I think I did this wrong. Should be this one, right? Oh, okay. So this is the free boundary. Okay, so it reflects without change of sign, right? And it forms a standing wave, and this free end is at the highest or at the amplitude actually. Okay, see it again. Okay, it reflects without change of sign. Okay. So yeah, already talked about this guitar string and how to compute the harmonics here. Okay, so you can the fundamental frequency is f1 and all the harmonics is of integer multiples of fundamental frequency. Okay. About wave impedance. Okay, we can talk about this later on. But let's take a break, and after coming back, I can show you some like real examples of how to generate computer sound using the physical model, and yeah, and we'll also talk about voice synthesis using the physical model. Okay. Let's take a break of 15 minutes. Let's get back at 3:40. Okay, 3:40. See you later.